So to get going again, we will have Ethan Park, who you heard from earlier, coming from USC, and we have Evan Wu from Elon University, and then joining virtually we have Priyanka Kaul from Harvard University, and they will be presenting their work on pitching in baseball.
Hi, everyone. Is it on?
One moment for Zoom difficulties.
They're having sound issues.
No, it was about showing the virtual speaker. I think we're just going to with this. All right, we're just going to go with this. We're good. We're good. All right.
Please use the handheld, the sound, they're having sound issues.
Yeah, you can use the
Handheld
lectern.
microphone, please.
No, the lectern works better.
For the other rooms?
Yes.
We're getting texted otherwise.
Yeah, no, that one works better.
All right.
Do it live.
So yeah, our project today is about utilizing interpitch dynamics to enhance pitch evaluations. And so we mean interpitch dynamics in the sense of like tunneling pitches, sequencing them off each other. That's kind of what we mean. Yeah, this is our team. I'm a senior at USC.
Hi, I'm Priyanka. I'm a junior at Harvard studying applied math.
And I'm Evan. I am a junior. I am Evan. I'm a junior statistics major at Elon University.
Okay, so like Ethan introduced, our project is a lot about interpitch dynamics and kind of wanting to explore pitching as an art rather than a science. As we all know, pitching is really important in the way that pitches sequence off each other and play off each other. A lot of the current pitch evaluation metrics for Major League Baseball pitchers have to do with pitches as individual entities. So they explore an individual pitch's speed, movement, and spin rate. What we were more interested in, however, is exploring how interpitch dynamics contribute to the effectiveness of a pitcher. For example, difference in speed between a pitcher's curveball and their fastball. This all plays into tunneling, deception, and really fooling a batter. Overall, our goal in this project was to improve effectiveness metrics and ratings using interpitch dynamics. And the two outcome variables we use to do this are xwOBA and run value per 100.
So the current kind of state of the art for interpitch models is Stuff Plus, but Stuff Plus does consider two specific interpitch dynamics, what we would consider interpitch, which are the velocity and vertical movement of a pitch with the fastball only. So we kind of went into the curveballs, sliders, other pitches besides the fastball. But if you're not familiar with Stuff Plus, it's basically a pitch evaluation tool. So each pitcher might throw like 3 different pitches, and Stuff Plus would rate each one separately. 100 is average for this metric, and for example, 110 would mean you're 10% better than average, 90 being 10% worse. It's constructed with an XGBoost model on these primary, I'm pretty sure this is just like a feature importance plot the creators created, and velocity difference with the fastball is the most important, second by vertical movement with the fastball. But you'll also see there's other important characteristics like just the raw pitch velocity and the spin rate. So this is a distribution of Stuff Plus by pitchers, and we see on the left it's grouped by pitcher, and on the right it's by pitch. And we see that the green line is 100, and we kind of have about 50-50 splits on each side, which makes sense. Our data that we used for this project was taken from the PyBaseball API, which is a Python API to grab like Savant data, Fangraphs, Baseball Reference, other types of data. And we also used Stuff Plus values we grabbed by ourselves from Fangraphs and some other individual StatCast features that we engineered.
So here are some of the league averages. You may or may not watch baseball, but a lot of you may not look at some of the actual underlying stuff. And so this is for each different type of pitch. And the way that you would read this, we can go by four-seamers, which is horizontal would be the horizontal movement in inches. Vertical would be the vertical movement in inches. It's worth noting that there is a stat called induced vertical movement. That is not this, so this would be 15 inches downward. The pitch proportion is for people who have four-seam fastballs. That's how much they, on average, use it. And then spin rate and speed in revolutions per minute and miles per hour. So, gotta stay here. So here is a decision tree using kind of the four main things that would make up a pitch. So that's how fast is it, how does it move up and down, and how much does it spin. And these are important because these are the values that we, for the most part, looked at in our inter-pitch models. So when we're looking at, for example, a fastball and how it relates to a curveball, we want to know how those movement profiles compare to one another. So I'm sure a lot of you are watching baseball at home and think, I want to know how spin rate for a slider relates to run value. And if that is what you're wondering, here we have it. So this is spin rate and also speed for sliders. And you can see that in general, the more it spins and the faster that it goes, the better the pitch is, which is pretty much common knowledge.
So our project was essentially split into three main models. First, we started really simple with an intercept-only model, which went by pitch type. Next, we moved to intra-pitch model, which is a lot of what is already out there. And to do this, we used a generalized additive model with Stuff Plus only, as Stuff Plus is a largely intra-pitch modeling technique. Finally, our third model, and the one that we were the most interested in, was the interpitch model. To do this, we use pitch differentials in speed and movement, for example, again, between a fastball and a curveball. And we threw these differentials into both a generalized additive model and a random forest. To strengthen both of these models, we included Stuff Plus as well. Finally, to compare all three models, we looked at their root mean squared errors and compared all of them to determine if interpitch dynamics really helped our modeling techniques.
So here is the final product, which is the interpitch random forest model. So to kind of explain exactly what that is, I know we've gone over that a little bit, but those are kind of fancy words sometimes. This is a model that takes into account how good a pitch is, what the pitch is compared to other pitches that the pitcher has, and the main part of a random forest model is that it's really heavy on interaction terms and utilizes those well. So for this model, okay, it's kind of blocking this in this one, but we have sliders, curveballs, and changeups, which are technically 2 to 3 pitches. So recently there has been a change to how sliders are categorized, and so there are slurves now and also sweepers. So we have those collapsed into the slider category. The curveballs also include knuckle curveballs, and the changeups include splitters. Notably, the variables that we used, we've mentioned before, but they're Stuff Plus, and then the differences between the given pitch that we are modeling and all the other pitches in that pitcher's arsenal. To train and implement the model, we used 5-fold cross-validation, which means that we cut the data into 5 pieces, kept 1 piece for later, used those other 4 pieces to predict that last piece, and did that 5 different times so that we could have a good prediction for all of the data. And then we evaluated it, as Priyanka said, with the root mean squared error. If you want to see kind of what that looks like, we have the observed and predicted values up here for a slider. A couple things to note here. It's not that related because the nature of pitches is that they are very varied in terms of what exactly they are and how they, I guess, influence how an at-bat ends and how overall effective the pitcher is. It is worth noting that for those of you who might not be familiar with root mean squared error, that is a unit-based thing, and so on average, the prediction was 0.046 away from the actual observed value, and that is WOBA, so that would be 46 points of x-WOBA.
Now this table just shows some of the root mean squared error values we got across our 3 main models. We wanted to point out specifically the highlighted green values. We found that our interpitch dynamic model worked the best on curveballs and sliders when we specifically used a random forest.
So we think there is a lot of room for improvement with this project. Specifically, there's some data that we didn't use, like the rates of all the combinations of sequences that a pitcher throws. So we had that data about like this pitcher throws the fastball and slider 32% and others 10%, but we didn't use that, and that was just a time constraint. We also need to kind of come through the data better in order to kind of get rid of really outlier predictions, which we kind of noticed when we were evaluating the models. They were like extremely outliered, and so that could be a source of error. We also want to reevaluate the use of GAMs, specifically on the interpitch model. So there might be a bit of a model selection problem here in the sense that when we looked at the data again, there wasn't the best justification for using GAMs because a lot of the features weren't like smoothly related between the feature and the response. So even if it's nonlinear, as long as it was like something that could be captured by the GAM, it would have been okay, but it was kind of weak. Lastly, we can, of course, always tune the model further, explore different approaches, and minimize that RMSC. But yeah. So the central idea of our project was that interpitch dynamics may hold some key information about how effective a pitch is going to be. And we still think that's true. But this approach is probably just not the right way to go about it. But Stuff Plus, this project also shows that Stuff Plus is very powerful. As you saw maybe on the earlier slide, a lot of the best performing pitches, models for pitches were just this second column, which is just a GAM of Stuff Plus, and that's probably like a really linear relationship, so this GAM is probably just a very like linear relationship it's capturing. And lastly, that our interpitch model that was based on a random forest was, one way of reading this table, I guess, is that it's the best at capturing the value or effectiveness of breaking balls, curveballs and sliders you see here. That's the two best. And yeah, thank you to our stakeholders, Sean, right there, from the Pirates, Dr. Ron Yurko, Meg Illingwood, Kwang Shamindra, who's now a doctor apparently. And yeah.
All right,
Question
thanks,
here.
guys. We have time for one question.
Question Steinberg.
Oh, Steinberg.
Okay, go ahead, Mike. So whenever you're looking at the effectiveness of pitches, I think that you have to really take into account what time the batter is up. Like I think that if you throw a first pitch curveball 3 times in a row, eventually they're going to catch on to that. So in what ways could you take into account the amount of times the batter's been up and also the amount of times the batter's seen that pitch?
That's a really good question. So a lot of the difficulty that we found in predicting pitches was that individual pitches that would often seem indistinguishable from one another did not necessarily merit the same results. So even if it was a first pitch curveball that was dotted right on the outside corner at the exact same speed and all that other different metric stuff, you might see anything from a home run to a called strike. And so we tried more so to focus on the seasonal values for a pitch. And so when we're talking about a slider, for example, in one of these models, we're looking at, say, Spencer Strider's slider, right? And so that would be overall for a season as opposed to an actual pitch. We would hopefully want to one day look at individual pitches and pitch by pitch data, but we elected not to go that route because the variability made it a little bit too difficult to predict actual results.
All right, thanks again.